ENVT4402 topics 9 to 11 risk, sensitivity analysis and Monte Carlo simulation. So in this lecture I'm going to give you an introduction to these three topics in preparation for numerical problem 3. So first of all we'll look at the distinction between endogenous and exogenous variables, and then we'll look at comparative statics and dynamics and what changes a model output, and have a brief look at risk management and Monte Carlo simulation. So we're going to make a lot of use of the fisheries model that we looked at in the last lecture, and we can do this to make the distinction between endogenous and exogenous variables. So if we look at the fisheries model, then we have an objective function which is there, so it's to maximize profit, and it's subject to difference equation constraint, the catch equation, some non-negativity constraints, and then you can split the model down into a set of parameters and some decision variables, which can be either the effort in terms of trawler days or the quantity of fish caught, and then there's a state variable. Now all the parameters we say are exogenous, and the reason that is that they're actually determined outside the model and then they're given and fixed. The decision variables are endogenous, and the state variable, because it's determined by the decision variables, is also endogenous. So for any model you can go through and you can identify some elements which are exogenous and the ones that are fixed, including here the carrying capacity, which I'd missed off. So you can split it up into things that are exogenous and fixed, and things that are endogenous, that are determined within the model, especially if you're looking at an optimization model. But this distinction is not always clear cut. For instance, the decision variables, the endogenous decision variables can be determined within the model, or they can also be fixed. So the distinction between endogenous and exogenous for things like decision variables can be a bit unclear in some circumstances. So starting off with comparative statics. Comparative statics is the comparison of two different economic outcomes before and after a change in some underlying exogenous parameter. Type of static analysis, it compares two different equilibrium states after the process of adjustment, if any. So if we look at the fishery management problem and we take the simplest static problem, and we change W, which is the cost of fishing effort, then this has the effect of pivoting the total cost curve round, and what that means is that the optimal solution goes from being at A to being at B. So you get by a change in the cost parameter, you get a change in the optimal solution. So that then means that the optimal level of effort, which in this example is endogenous, is being changed by the change in the cost parameter W, which is exogenous. So we've got a change in an endogenous variable E, due to a change in an exogenous variable W. So there's a couple of questions you can ask about this. So first, what is the direction of change? Well, we can see here that effort is going down. So as the cost of effort goes up, then the level of effort goes down. Is it so in our example it's negative? Is it expected to be monotonic, always positive or always negative? Well, in this case we're expecting it to be always negative, and then the next step is to look at this measure of responsiveness, which is called an elasticity. So an elasticity is just a general measure of responsiveness. So it gives us the percentage change in some variable I divided by the percentage change in some other variable X. And so typically when we're looking at this, X can be exogenous and Y can be endogenous. So in the previous example, then we could say we want to look at the percentage change in the effort due to a percentage change in W. So that's how we can interpret it. And another way of interpreting this is to fix the percentage change in the denominator as always being 1%. So that means you can say, well, what's the percentage change in effort with respect to a 1% increase in W. So that's an easy way of interpreting an elasticity. So if we find the elasticity is greater than 1, then it means the change is positive, and it also means it is elastic or responsive. So for a 1% change in 1% change, for instance, in W, then if the value turns out to be greater than 1, then we're getting a greater than 1% increase in the effort. Of course, this is not the case, but that's what it would mean. And then if the elasticity is in this range here between 0 and 1, then the change is positive but inelastic or unresponsive. And then we've got the negative versions of those. So if we got a negative value which is less than -1, so for instance -2, then it's negative and elastic, and it's responsive but in a negative direction. And then if it lies between 0 and -1, then it's negative and inelastic. And then there's two borderline cases. Elasticity is equal to 1, elasticity is equal to -1, which are unit elastic. Okay, so that's elasticities. Now, elasticities are incredibly useful because they give us a way of measuring the responsiveness of a change in one variable caused by another. So they're very generally applicable in economics and in science, just as a quick summary measure of how responsive a change is. And the great thing about them is that they don't actually involve any units, so they're what's called unit free. So here's an example of a comparative static analysis. So we're looking at the relationship between we're looking at the effect of the stock of fish and the quantity of fish caught, and the exogenous variable we're interested in is the discount rate. Okay, so so if we set the discount rate equal to 0, then hold with everything else held constant, then what happens is that we get a relatively high stock of fish. So if R equals 0, then the stock is around about 550. As the discount rate increases, then the stock falls, and the harvest rate increases, and then it reaches a turning point. And as we head towards a discount rate of 0.1, which is 10%, then the harvest rate falls. So we get, in this case, we get a monotonic response to the discount rate to the stock, in that as the discount rate increases from 0 to 10%, the stock is falling, but we get a non-monotonic response of the harvest, in that initially the harvest rate is increasing and then it's falling. Comparative dynamics. So in the last example, we were looking at the fishery in a steady state, and that's where the stock is not changing through time. Comparative dynamics is where we're looking at the whole time path for a variable, instead of just looking at single points in time. So this is relevant to a number of resources. It's relevant to fisheries, and it's also really relevant to mining. And the thing with mining is that there is no steady state. So it's a characteristic of mining that a mine just cannot have a steady state. With a fishery, you can have a fishery which is out of equilibrium, but and then it follows a dynamic path, and we can do comparative dynamics on that, but it might be heading towards a new equilibrium steady state. So here's an example of extraction from a mine, and the details aren't important here. We're looking at the effects of a high discount rate and a low discount rate. So with a high discount rate, extraction, which is QT, so that's the extraction. Sorry, that's terrible. So that is extraction. So the time path is this one here, and we can see that extraction starts high and then falls rapidly, and the stock is exhausted at time t dash. So t dash and t dash dash are time of exhaustion of stock. If we then compare that with the low discount rate, we start with a lower rate of extraction, then we follow this path down, and we see that the time to exhaustion of stock is much later. So there's no simple elasticity to compare these two time paths, but they could be compared in terms of the initial level of extraction. So that's one thing they can be compared for. You could compare the different rates of extraction at different points in time, and you could compare the time to exhaustion as a way of comparing the two time paths. But they don't. Comparative dynamics is much more complicated, so it's harder to compare time paths than it is a single point. And here's another example of comparative dynamics. So in this case, the exogenous variable price is set at two different levels, and the starting point for the fisheries is the same. It's here. So the fishery starts life here with a stock of around about 600. We can then see that even with different prices, then the trajectory is pretty much the same as it heads rapidly down here towards a steady state, and there's a slight difference between the two steady states, and then there's a slight divergence after the steady state as the stock and the harvesting reach the final period, which is in period 20. So this is an example of where comparative dynamics is applied to a fishery problem, and there you're looking at different time paths, which might include moving towards a steady state, or possibly staying close to a steady state for a period of time before diverging away to a final value. Okay, so risk management. So this is quite a brief introduction, and we'll talk a bit more about this in the seminar, and also in the lecture in the final week. So most decision makers are risk averse. This means that they would tend to select certain outcomes over risky outcomes with the same expected value. Risk aversion is a bit like the discount rate. It's an important individual parameter and determines our attitude to savings, insurance, gambling, and other forms of risk taking and risk avoidance. So some people like to gamble, other people like to take out every insurance policy possible. Risky choice often involves selecting between distributions of outcomes. So for instance, if this is a probability distribution function, then that represents quite a risky distribution. That distribution represents a less risky distribution, and so risk averse individuals might prefer this distribution over this distribution. So this very flat distribution might be is likely to be viewed as inferior to this less risky, tighter distribution here. Choice of things like fishing quota and pollution management determines the distribution of outcomes. So this is an important point, in that if we decide on something like a fishing quota, then that's going to determine the profitability of the fishery, but it's also going to determine how sustainable and how resilient the fishery is. And an important thing in fisheries management and in environmental management is avoiding extreme events such as collapsing a fishery or permanently damaging a river ecosystem. So to address these problems, there's a method called Monte Carlo simulation, and this is an incredibly complex method from statistics, and it's also very widely used in topics like chemistry, in subjects like chemistry and physics, and it has lots of sort of complicated models and methods. We're going to use it really quite simply here. So if you've analysed a model such as a fishery model and you've come up with an optimal solution, then the question is, well, just how robust is this model to assumptions? So for instance, if the fishery growth in reality is highly variable, what happens to your fishery through time if that parameter varies? And then you could extend this, so you could apply it to the fishery growth parameter. You could apply it to the carrying capacity. You could apply it to the catchability coefficient if you wanted. So you could do those individually, or you could do them all together to try and reflect the sort of level of risk that a fishery system faces in practice. The other thing you can do is you can use this to identify critical stock values, and also the probability of critical values being exceeded, or for instance the probability that the stock is below some critical value. So what we're going to do here in this example is we're going to draw. We're going to take draws from the growth parameter, sometimes called the intrinsic growth parameter, in the fishery model, and we're going to draw values between 0.2 and 0.4, and we're going to draw 10,000 of those values from a uniform random distribution. So those draws will look something like this. So you see that they don't exactly replicate the uniform distribution, but it's pretty close. So a uniform distribution is one where the probability of drawing values between two extremes is the same. So that gives you the probability there. And of course, if we sum up under there, then that area is going to equal 1, because we're looking at so if we sum up under there, then that's going to equal 1, because we're looking at a probability. Okay, so here's how the example is applied to the fishery model, and there's full details of this given in the code for numerical problem 3, and I've also gone through this in the lab for numerical problem 3. So what we see is that as we simulate forward the fishery model, and we're running through the difference equation for growth and catch, and we've set Q at some fixed value which is meant to be simulating a quota, then this generates a distribution of stock levels that becomes wider and wider through time. So initially we're starting at 400, and we've got quite a narrow distribution, and then as we go through time, the 2 years, 6 and 8, then the distribution becomes wider and wider. So over a 10-year period, what we could do is we can plot out the final distribution, and we can see that the distribution of stock has now approximated a normal distribution, despite the fact that the gamma parameter was actually drawn from a uniform distribution. We can also look at the present value of profit to see how profitable the industry is, and that's interesting because actually the profit varies much less than the stock. So with the stock, it's going from a value there of about 560 down to as low as 250, and here the profit is just going over a 10-year period is just going between 56,000 and 56,140. So interestingly, the profit has a much narrower range. We can take the final values and do statistics on those values. So the mean value for the stock is 414. The standard deviation is 51.7, and the lowest 25% is below 379.909. We can also work out the weight in the tails. So the percentage of observations below 300. So say that is a critical value. So, and if we approximate the distribution of stock by a normal distribution, then that's saying that if that's the critical value of stock at 300, then the weight that there is in that tail is only 1.59%. So in this case, it's quite a small weight. That means that only around about 1.5% of the time would the stock be below 300 tons. So just to summarize, change in exogenous parameters such as the discount rate and the cost of fishing efforts leads to comparative static and comparative dynamic analysis. Risk management is more about distributions and simulation and working out whether optimal solutions are too risky, and if the conclusion of the regulator is that they are too risky, then that suggests that the decision variables have to be changed. Monte Carlo simulation is a way of estimating the risk linked to optimal and simulated solutions. So we get information on another dimension other than just the optimal value. We ask the question: is the level of risk associated with this optimal value acceptable? Two references: Brandimart, which is available online, and Panel 1997, which is a straightforward introduction to sensitivity analysis. We'll be going through that in the seminar.